Okay, I hope I'm audible to all students who are attending this lecture of Intermediate Microeconomics Part 2. We intend to discuss some of the problems based on game theory from the book Snyder and Nicholson. Okay, so in this particular lecture, I will be solving some of the back problems from the book Snyder and Nicholson based on the concept of game theory. Okay, so let's look at problem 8.1. Okay, so consider the following game. All students can see the matrix on their screens. Okay, this is player 1, this is player 2. Player 1 has strategies A, B, and C, and player 2 has strategies D, E, and F, and we are given the payoffs. Okay, part A asks us find the pure strategy Nash equilibrium, if any. Part B asks us to find the mixed strategy Nash equilibrium, in which every player is going to randomize over just the first two actions. Okay. Part C asks us to compute the expected payoffs of the players in the equilibrium. Okay. And part D asks us to draw the extensive form for this game. Okay. So let me come to the whiteboard and let's solve this question on the whiteboard. So we look at Snyder and Nicholson problems based on game theory. Okay, so we look at the first question and I'm drawing the matrix on the screen. We are given two players, player 1 and player 2. Okay, player 1 has the following strategies A, B, and C. Player 2 has the following strategies D, E, and F. The payoffs of both the players are given to us as follows. The first payoff always depicts the payoff for player 1 and the second payoff always depicts the payoff for player 2. Okay. So I am writing the payoffs which are given to us. And now let's first of all find out the pure strategy Nash equilibrium. Okay. So our objective is to find the pure strategy Nash equilibrium. So remember, pure strategy Nash equilibrium is that action profile such that every player's action is the best response to the other player's action. Okay, so first of all, let us see whether A comma D is the Nash equilibrium profile or not. Let's check that. So suppose player 1 plays A, then what will player 2 do? Player 2 is going to play E, because when player 1 plays A, player 2 gets the highest payoff from playing E. Compare the payoffs 6, 8, and 0. You can clearly see that 8 is the highest. So player 2 is going to play E. So that means this is A comma D is not the Nash equilibrium, because when player 1 plays A, player 2 is not going to play D. She is going to play E. And when player 2 plays E, what will player 1 do? Player 1 is going to play B, because look at the payoffs. When player 2 plays E, player 1 gets 5 from A, 7 from B, and 1 from C. So player 1 is going to respond by playing B. So this is also not the Nash equilibrium. This is anyways not the Nash equilibrium because none of the players chose F when the other player was choosing its own action profile. So that means A comma F is not the Nash equilibrium. Okay. Then let's look at player 1 playing D. When player 1 plays D, player 2 responds by playing D, right? Because if you look at the payoffs, player 2 gets 8 from D, 6 from E, and 1 from F. So when player 1 plays B, player 2 responds by playing D. But when player 2 plays B, player 1 responds by playing A, because player 1 gets 7 from A as compared to 5 and 0 from B and C. So this is not the Nash equilibrium. Okay, this is anyways not the Nash equilibrium because there's a tendency to deviate, and this was never chosen by any of the players in response to the other player. This is also not the Nash equilibrium. Okay, let's look at the next possibility. Suppose player 1 plays C, then player 2 is going to respond by playing F, because player 2 is going to get 0 from D, 1 from E, and 4 from F. 4 is the highest payoff for player 2. So player 2 is going to respond by playing F. And when player 2 plays F, player 1 gets 0 from A, 1 from B, and 4 from C. 4 is the highest for player 1. So player 1 is going to respond by playing C. So we got a dash below both the payoffs. That means our only Nash equilibrium is C. Remember, this is also not the Nash equilibrium, and this is also not the Nash equilibrium. By Nash equilibrium, I don't mean the payoffs. By Nash equilibrium, I mean that A comma D is not the Nash equilibrium. A comma E is not the Nash equilibrium. A comma F is not the Nash. B comma D is not the Nash. B comma E is not the Nash. We have eliminated all of these. B comma F is also not the Nash. C comma D is not the Nash. C comma E is not the Nash. Therefore, I can write C comma F is the unique pure strategy Nash equilibrium. C comma F is the unique pure strategy Nash equilibrium. Because whenever player 1 plays C, player 2 is going to respond by playing F, and when player 2 plays F, player 1 is going to respond by playing C. So this is going to be the unique Nash equilibrium. Remember, 4 comma 4 is not the Nash equilibrium. C comma F is the Nash equilibrium, and the players are getting a payoff of 4 in the Nash equilibrium. Okay, so hoping all students have understood this part. Then let's look at part B. Part B is asking us to find out the mixed strategy Nash equilibrium. Okay, so first of all, guys, before doing part B, let's look at part C, because if you look at part C, what is part C asking us? So first of all, what is the payoff both the players are getting? So I can write, so some part of part C I'm solving in part A only. So I can write that clearly in the pure strategy Nash equilibrium, both player 1 and player 2 get a payoff of 4. Both player 1 and player 2 get a payoff of 4. So this is my part C. Some part from part C I've already solved it. Okay. Now let's look at part B. So if I come back to the assignment, what was part B? Find the mixed strategy Nash equilibrium in which each player randomized over just the first 2 actions. So that means player 1 is going to play A and B with some probability. Player 2 is going to play D and E with some probability. So they are randomizing over the first 2 actions only. So I come back to the whiteboard, and now what we are doing is I am erasing C and D. I am erasing C and F because we are strictly given that the players are randomizing over the first 2 actions. So I erase this off, and I can write, so erasing this part also. Now our objective is to find the mixed strategy Nash equilibrium of this particular game. So I erase this also. Let the matrix look nice and clear to everyone. Okay. So now this is our matrix where the players are randomizing only over their first 2 actions. So in the mixed strategy Nash equilibrium, again, I can say that suppose player 1 plays A with probability P and B with probability 1 minus P, and player 2 plays B with probability Q and E with probability 1 minus. Okay, so I can write, suppose in the mixed strategy Nash equilibrium, suppose in the mixed strategy Nash equilibrium, player 1 plays A with probability P and B with probability 1 minus P, and player 2 plays D with probability Q and E with probability 1 minus Q. Okay, so now let's look at player 1, guys. So player 1's expected payoff from A. player one's expected payoff from A. What is the payoff player one gets from A? So player one is going to get a payoff of 7 when player two plays B, which happens with probability Q, and player one is going to get a payoff of 5 when player two plays E with probability 1 minus. So player one's expected payoff from A is 7Q plus 5 minus 5Q, which is 2Q plus 5. Similarly, guys, we can calculate player one's expected payoff from B. Player one's expected payoff from B will be player one is going to get a payoff of 5 when player two plays B with probability Q, plus player one is going to get a payoff of 7 when player two plays E with probability 1 minus 2. So I can write 1 minus 2 here. So that is going to become 5Q plus 7 minus 7Q, which is 7 minus 2. So now, guys, when will player one be indifferent? So I can write player one will be indifferent. Player one will be indifferent between playing strategies A and B if the expected payoff of player one from A, which is 2Q plus 5, is exactly equal to the expected payoff of player one from strategy B, which is 7 minus 2. I can solve for Q. So 2Q plus 2Q is equal to 7 minus 5, which implies 4Q is equal to 2, which implies Q is half. So we have got Q star as half. Therefore, 1 minus Q star will be half. So solving for player one, we have got the probability with which player two is going to randomize over D and E. So Q star and 1 minus Q star are half and half respectively. Okay. So hoping all students have understood this. So I can write, using this, guys, I can write the best response function for player one. Now look at the best response function for player one. So clearly you can see that when Q is equal to half, then Q is exactly equal to half. Player one is indifferent between playing A and B. That means P lies between 0 and 1. When he is indifferent between playing A and B, it means he'll play both A and B with some probability. So P lies between 0 and 1. Okay. When Q is greater than half, what is going to happen? Okay. You can clearly see that when Q is greater than half, when do we get Q greater than half? If expected payoff from A is more than expected payoff from B. That means if I say that expected payoff from A, which is 2Q plus 5, is greater than expected payoff from B, when you solve this, guys, you will get Q greater than half. And when expected payoff from A is greater than expected payoff from B, player one is going to play A for sure. For sure means P will be equal to 1. And what will happen when Q is less than half? How will you get Q less than half? How will you get Q less than half? Very simple. Just do the reverse. So on the top, you can see if the expected payoff from A, which is 2Q plus 5, is less than expected payoff from B, which is 7 minus 2Q, you solve this, you will get Q less than half. And if expected payoff from A is less than expected payoff from B, player one is going to play B for sure. When player one is going to play B for sure, it means 1 minus P is equal to 1. If 1 minus P is equal to 1, it implies P is equal to 0. So this is our best response function for player one. So hoping all students have understood this. When Q is exactly equal to half, player one is indifferent between playing A and B. So P lies between 0 and 1. It means he is going to play A with some probability and B with some probability, where P lies between 0 and 1. When Q is more than half, player one's expected payoff from A is more than B. So player one is only going to play A, which means P is equal to 1. If Q is less than half, it means for player 1, expected payoff from A is less than expected payoff from B. So player 1 is going to play B for sure and not A. When player 1 is not playing A for sure, it means P is equal to 0. Player 1 is only going to play B. Another way of saying it, if player 1 is going to play B for sure, 1 minus P is equal to 1, which implies P is equal to 0. Okay, now on similar lines, we can quickly calculate the player 2's expected payoff. Okay, so I can write on similar lines, player 2's expected payoff from D. Player 2's expected payoff from D is how much? Player 2 gets a payoff of 6 when player 1 plays A with probability P, plus player 2 gets a payoff of A when player 1 plays B with probability 1 minus. So this is going to be 6P plus 8 minus 8P, which is going to be 8 minus 2P. Okay, and similarly on similar lines, I can write player 2's expected payoff. Player 2's expected payoff from E is how much? Player 2 gets 8 when player 1 plays A with probability P, and player 2 gets 6 when player 1 plays B with probability 1 minus P. So this is going to be 8P plus 6 minus 6P, which is going to be 2P plus 6. Okay, so this is player 2's expected payoff from D. This is player 2's expected payoff from E. When will player 2 be indifferent? So I erase this off now. Erasing this off, I can write that therefore player 2 will be indifferent. Player 2 will be indifferent between playing D and E if player 2's expected payoff from D, which is 8 minus 2P, is exactly equal to player 2's expected payoff from E, which is 2P plus 6, which implies 8 minus 6 is equal to 4P, which implies 2 is equal to 4P, which implies P is half. So I get P star as half. So 1 minus P star will also be half. That means player 1 is going to play A with probability half and B with probability half. On similar lines, guys, now I can write the best response function for player 2. Okay. So let's now write the best response function for player 2. So I'm erasing this part off. And on the top, I am writing best response function for player 2. So what will be our BR2, guys? So you can clearly see that when P is equal to half, then player 2 is indifferent between playing D and E. That means Q lies between 0 and 1, because with some probability, player 2 is going to play D, and with some probability, player 2 is going to play E, right? But what happens when P is greater than half? When will I get P greater than half? So understand this, guys. If I say that expected payoff from D is less than expected payoff from E, that means if I say that 8 minus 2P, which is my expected payoff from D, is less than expected payoff from E, which is 2P plus 6, you can solve this. You will get 2 less than 4P, which implies P greater than half. So for player 2, when expected payoff from D is less than expected payoff from E, player 2 is going to play E for sure. E for sure means 1 minus 2 is equal to 1, which implies Q is equal to 0. Q is equal to 0. Okay. And guys, when P is less than half, exactly the opposite is going to happen. When will I get P less than half? I will get P less than half if the expected payoff of player 2 from D is greater than expected payoff of player 2 from E. In this case, if you solve, you're going to get 2 greater than 4p, which implies p is less than half. So when for player 2, when the expected payoff from D is more than expected payoff from E, player 2 is going to play D for sure. D for sure means Q is equal to 1. So we have drawn the best response function. We have written the best response function for player 1 and player 2. Now I can draw the best response functions graphically also. So I'm erasing this part off. Although we have found out the mixed strategy Nash equilibrium, but still let's plot both the best response functions in a graph. So erasing this off. So let us draw the best response function. So this is P and this is Q. P also lies between 0 and 1. Q also lies between 0 and 1. Let's plot the best response function of of player 1 first. So when Q is equal to half, P lies between 0 and 1. When Q is equal to half, P lies between 0 and 1. When Q is more than half, P is exactly equal to 1. You can see that when Q is more than half, P is exactly equal to 1. So a vertical line here. And when Q is less than half, P is equal to 0. So this is 0. P equal to 0 is this. So this line, and this line depicts the best response function for player 1. Similarly, I can write the best response function for player 2. I can draw that. I'm using red color for it. When P is equal to half, Q lies between 0 and 1. So this is my P equal to half. When P is equal to half, Q lies between 0 and 1. Okay. When P is greater than half, Q is equal to 0. So this part. When P is greater than half, Q is equal to 0. And when P is less than half, which is this, Q is equal to 1. So Q is equal to 1 when P is less than half. So this is the best response function for player 2. Where is the Nash equilibrium happening? All students can clearly see that this is my mixed strategy Nash equilibrium. The intersection of the two best response functions gives me the mixed strategy Nash equilibrium. So I can write in the mixed strategy Nash equilibrium, player 1 plays A with probability half and B with probability half, and player 2 plays B with probability equal to half and E with probability equal to half. So I can write the answer for this question is the mixed strategy Nash equilibrium is P star Q star is equal to half comma half. Is the only mixed strategy Nash equilibrium. So hoping all students have understood how we have found out the mixed strategy Nash equilibrium. Okay. And then if I ask all students, what is the expected payoff the player 1 and player, what are the payoffs which player 1 and player 2 are getting? Okay. So you can even calculate the payoffs. That is something which is very easy. So you just have to put P and Q as half in the expected payoffs, which we had written a few minutes back. So I can erase this and I can write the expected payoffs. So erasing this part off. I'm erasing this part off and we can write the expected payoff. So I can write expected payoff for player 1. Expected payoff of player 1 from A is how much? 7 times Q plus 5 times 1 minus Q. In this, guys, just put Q as half because we have found out that Q is half. So what do I get? 7 by 2 plus 5 by 2, which is 6. And similarly, what is the expected payoff player 1 gets from D? 5 times Q plus 7 times 1 minus Q. We had written this payoffs a few minutes back. Again, put Q as half. That is our equilibrium. So 1 minus half is half only. So again, we get 6. And similarly, guys, you can write the expected payoff of, you can write the expected payoff which player 2 is getting. So I can write expected payoff for player 2 from D is 6 into P plus 8 into 1 minus P. 6 into P plus 8 into 1 minus P, which we had written a few minutes back. Just put P as half. So 1 minus half is half only. 6 plus 8 is 14. 14 by 2 is 7. And similarly, I can write expected payoff of player 2 from E is again 8P plus 6 into 1 minus P. 8P plus 6 into 1 minus P. Again, you put P as half, you get 7. So player 1 gets a payoff, expected payoff of 6 from both A and B in Nash equilibrium, mixed strategy Nash equilibrium, and player 2 in the mixed strategy Nash equilibrium gets a payoff of 7 from both D and E. Okay, so if I come back to the assignment, we have solved part A, we have solved part B, and we have found out the player's expected payoff in the equilibrium. Draw the extensive form for this game. Extensive form is nothing but the tree. We can draw the tree for this game. So I erase this particular part off, and we can draw the extensive form for this game also. Okay, so if you look at the extensive form for this game, okay, the extensive form is as follows. Okay, so let's look at the extensive form for this game, which is going to be a tree. Okay, so I can draw the extensive form as follows. Player 1 has 3 strategies A, B, and C, and corresponding to every strategy, you have a decision node of player 2. Okay, you have the decision node of player 2, and player 2 further has 2 strategies D and E. D, E, and F. D, E, and F. Okay, so here also I have player 2 has 3 possibility, has 3 strategies D, E, and F, and here also I have the decision node of player 2. He has 3 strategies D, E, and F. And we can write the payoffs, guys. What were the payoffs? When player 1 plays A and player 2 plays B, the payoffs are 7, 6 to player 1 and player 2 respectively. When player 1 plays A and player 2 plays E, the payoffs are 5, 8. And when player 1 plays A and player 2 plays F, although F is not there, but you can see in the original question, it is 0, 0. Similarly, when player 1 plays B and player 2 plays D, the payoffs are 5, 8. When player 1 plays B and player 2 plays E, the payoffs are 7, 6. When player 1 plays B and player 2 plays F, the payoffs are 1, 1. And similarly, guys, when player 1 plays C and player 2 plays D, the payoffs are 0, 0. When player 1 plays C and player 2 plays E, the payoffs are 1, 1. And when player 1 plays C and player 2 plays F, the payoffs are 4, 4. So this is our extensive form for the game. Okay. So hoping all students have understood this is the extensive form for the game. But understand this, guys, if I say that it's a simultaneous game, since it's a simultaneous game, I am going to connect the decision nodes of player 2 using dots. These dots are going to represent the fact that player 2 does not know what player 1 has played. Remember, it's not a sequential game. If it was a sequential game, I would have not drawn this dotted red line. I would have not drawn this dotted red line if the game was played sequentially with player 1 moving first and then player 2 moving. But since it's a simultaneous game, so I have drawn the extensive form for the simultaneous game, where the game is played simultaneously between players 1 and 2. So player 1 has 3 strategies A, B, and C, and corresponding to every strategy comes the decision node for player 2, where player 2 further has 3 strategies D, E, and F. Okay, in this particular part, I have not mentioned F, but you have F also and you have C also, which was there in the initial part A. So if you look at the question carefully, this is going to be the extensive form. I am again revising. The reason I have drawn a dotted circle around the decision nodes of player 2 is because player 2 does not know what player 1 has played, because the game is a simultaneous game. This is not a sequential game. If it was a sequential game, everything else would remain the same, but I would have not drawn this dotted red line connecting the decision nodes of player. But the moment I draw this dotted red line connecting the decision nodes of player 2, it simply means that it's a simultaneous game. When player 1 plays a strategy, player 2 does not know that. Okay, so this is where I intend to stop in this particular lecture. So what we have covered in this lecture, we have done the first problem from the Snyder and Nicholson back problems based on game theory. Okay, we'll start our discussion from problem 8.2 in the next lecture for the practice based on game theory. So I stop in this particular lecture. I hope all students have enjoyed this lecture. Any doubt, you can unmute your mic and ask, or call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop in this lecture.